Hey everyone, welcome back. Let's try out an example now, going back and forth between mass and mole fractions. This is just one of those times where I really want to show you how to do this again and again and again so you can get used to it. So, what do we have? We've got a gas mixture, who would have guessed, and it has 34% oxygen, 44% nitrogen, 22% carbon dioxide, and it's on a mass basis. So, those are all my mass fractions right there. We're going to determine the volumetric analysis of the mixture and the apparent gas constant. Okay, what's the molecular weight of my mixture? What's the gas constant in my mixture? And what's the mole fraction of all these things? And it says that, hey, I can go to the tables to find my molar mass, my gas constant, and critical point properties. All these things are going to be necessary. If you're watching online, this is where a textbook really comes in handy because they have these. But you can usually find these things in like the guides for the FE exam. Like your FE exam has a big equation sheet. It's going to have those in there as well. So there's lots of easily available references you can use to find these. That being said, let's jump into it. So first off, we need to calculate the mass and the number of moles so we can get our mole fractions. Now, for me, what I do when I'm trying to do this just so I have an easier time working with it is I just choose a number for the mass. It's not given. I gave it on mass basis, so it's just all fractions of it. So I'm just going to choose 100 kilograms. Why 100 kilograms? Because it just works really nicely for me. It's a percentages. What's 34% of 100? It's 34. It's really simple. So from that, I can go ahead and find the mass of each of those components. Well, 34% of 100 is 34 kilograms. And then for nitrogen, 44 kilograms. And for carbon dioxide, 22 kilograms, all the way down the line. So once you've done that, you can then figure out how many moles you have of each of those individual things. If you wonder to yourself, what if I pick the wrong mass? If it doesn't give it to you, if it just gives it to you in a mass fraction, it doesn't matter because you're just solving everything on a per unit mass basis, more or less. And so it doesn't matter how big or small you get, as long as it's a well-mixed mixture, which we're assuming it is, it's going to have the same composition. Okay, so moving onward. To figure out the number of moles, you have to take the mass of that individual component and divide it by the molecular weight. So for these molecular weights, that's where you need to go to a periodic table if you don't know them off the top of your head. Oxygen is equal to 16, nitrogen is equal to 14, and carbon is equal to 12. That's just some good ones to memorize because you're going to see them a ton. Also, H is equal to 1. And if I have N2, well, that's just times 2, O2 times 2, CO2, well, I have carbon plus 2 of these. And that's how we get our molecular weights. It's really helpful to have just a few of these memorized. Beyond that, don't worry about it, just go to your periodic table. If you're wondering, well, it doesn't say exactly 16. You're right, for oxygen it's like 15.999, but you can round here and the answers will be so close, it won't matter. So with that, I get the number of moles for each of these components. So if I want to get a mole fraction, this is where I can do it because I now have the moles for all of them. I can find the total number of moles from a mixture, which is just about 3. And then from that, I can find the mole fractions. So this is just me taking their individual number of moles and then dividing it by the total number of moles. As a note, you will not normally see the same number. The fact that we have 34% here for oxygen, that's a coincidence. That's not going to happen all the time. And you can see that it didn't match up for nitrogen or carbon dioxide. Okay, so we have 33.9%, 50.14%, and 15.95%. So this is the volumetric analysis. We just finished it. If you're wondering, well, why isn't it like a molar analysis? Why do they call it volumetric analysis? The more moles of gas you have, the more volume you take up. It doesn't matter what the size of those little balls are. The size of the balls compared to the volume they're taking up is just infinitely small. So it doesn't actually matter that technically oxygen is way bigger than hydrogen for that. The volume they take up is based on the number of moles. More gas, more volume. Okay, so now let's go ahead and start calculating the molar mass of the mixture because that's how we're going to get that gas constant, the apparent gas constant for our mixture. How do we get the molar mass of the mixture? Well, I take the mass and I divide it by the number of moles. That's the first way I can do it. And that's the easiest way to do it. So I'm going to do it that way. So I have a mass of 100 kilograms. That's what I use for getting all these numbers, so I need to keep on using it. And I divide it by the number of moles, which was 3.133. I get a molar mass of my mixture of about 32. So what this is showing me is that I've got a lot of oxygen here, and that's more or less dominating the mass. Also got quite a bit of nitrogen, that's 28, and I've got carbon dioxide, which is 44. So that's what's helping us to get around there. It's kind of averaging out. So I now have the molar mass of my mixture. To find my gas constant, I simply take my universal gas constant, which is 8.314 or 8,314, just depends on which units you're using, and I divide it by 31.91. And that gives me my final specific gas constant for my mixture of 0.2606. Okay, so one thing I want to go ahead and do is I want to show you, let's see here. It says use a table containing the molar mass, gas constant, and critical point properties. I want to go ahead and show you where that is before we finish this problem and move on. So, with a little bit of movie magic, we're going to jump to our textbook. Okay, so here we are once again in our McGraw-Hill textbook. And so I'm going into table A1. That's the one that has the molar mass, gas constant, and critical point properties. Let's see if the HTML works. It's actually recently closed. Nice. So right here I can see the molar mass. Oh my goodness, I said 14 earlier. My goodness, I was way off. 28. I knew it was close to nitrogen. I was picking the atomic nitrogen rather than molecular. Oh well. That's why you don't do things off the top of your head. By the way, I can find other things too. So I can find, let's see, go down here. I can find hydrogen right there, 2, because it's usually H2. I can find oxygen right here. For most of these problems, you can round. You don't have to do the full amount of decimal places. Don't go crazy on it. And here's nitrogen. So all of these are here and available to you. You can find them. You can pull them out here so you can use them in your problems. Don't worry about having to just know what these are or going to a periodic table. You can do that, but it's right here for you. So that's it for this video. Thank you all for watching. I'll see you all next time as we continue to work through chapter 14. Have a good day. Bye-bye.